out this next one, the negatively skewed. So we come over here, we've got a fat tail on the negative side. I don't know if I drew that very well, did I? So that's a fat tail on the negative side. What is causing the difference between the mean and the median? So the mean is less, right? So the mean is here. This is the mean. Mean. Alright, and then the median is up here. Why is the mean lower than the median? Yeah, a large group of really, really poor people, could be. But more importantly, like you said, compare. Right? There are poor people in all three of these towns, but relative to the rich people, these people are really, really poor. That is pulling the mean down. Is it accurate to say that there are more poor people?
Yeah.
No, they're just really, really poor.
Oh.
The ones who are poor are really, really poor. Not necessarily more of them. And what might be causing the skewed distribution of the wealth? Yeah, maybe a factory left all of a sudden, and then you've got a bunch of unemployed people.
Divorce.
High divorce rate in this town. Could be like a retirement community, maybe. It doesn't have to be a depressing scenario. Could be a bunch. What's that?
Eli Manning.
Eli? Or what happened? He's getting, okay. He's not, he's still rich though, right?
But he getting banked, so he won't pay for that game, so he lost money.
Does he get paid per game that he plays?
You get paid.
No, I get a contract.
You get paid per game. You get paid per game.
Are you serious? So if he doesn't start,
What sport is this?
But that's probably in his contract though. If he doesn't start, if he starts, he gets paid more.
What sport is this?
What's that?
What sport is this?
Oh, football.
Oh, football is by performance. It's not by contract. So if they don't fully perform, if they get injured, they don't get paid. In the NBA, if they get injured, they can still get paid.
So in the NFL, they get injured, they don't get paid?
Absolutely.
Like zero?
Nada.
If you bench, you don't get paid.
Exactly.
So
NBA,
That is crazy.
in NBA, that's why I asked the sport. In NBA, you do get
Contracts are
paid.
not guaranteed, so they can cut you any time and they won't fix that.
That is crazy. Such a violent sport to begin with.
Absolutely. I rather like NBA, I'm sorry.
All right. Good stuff. Okay, you okay to keep going here? We'll take a break at some point, but I feel like we're okay to keep going a few more minutes.
Few more
All right.
minutes.
Oh, I got another less depressing scenario.
Oh yeah.
Maybe their expenses are not so high, so they don't have to work as much. So.
Okay, so a bunch of people who moved to this town because low cost of living.
Yeah.
Oh my.
Yeah.
That could be it.
That's fantastic. All right, good point. All right. All right, so we're warming up to normally distributed data, and that's what we'll talk about for the entire class. But in order to put that in a frame of reference, we just went over some examples of non-normally distributed data. And it just makes us think about what's different and why and how. And now we'll turn our attention for the rest of the class to the normal bell curve. Because if we can assume things are normally distributed, we can make certain assumptions that are exciting and useful. And we'll talk about when it's safe to make those assumptions and what they are. One more thing we need to be clear on before we get to the normal distribution is this concept. Take a look at this graph, this slide. Tell me what is the difference between these two normally distributed frequency distributions. Mean, medium, and the mode are all the same.
Right. Oh, it's how it's spread. So it's certain. It's like the quality, the outcome part is shorter, longer than the
Outcome part is shorter in one, longer than the other. All right. Now suppose this was a frequency distribution of income, just like we're discussing.
I think it has to do a lot the quantity and this this two graph.
Yeah, okay, so the quantity is different.
Space.
Yes.
Absolutely, that is correct.
But even the frequency of the probability cause, even though they got the same loop, one is higher than the other again.
Yeah, alright, so the chances of you being an average person in this town are much higher.
Right.
Yeah, okay. So what else can you tell me? What else is different about these towns, perhaps, in income
More
distribution?
people.
Suppose it's the same number of people.
Okay,
So more people have the
He-
same amount of income?
More people have the same amount of
I
income.
was gonna say that for the right one, and then on the left one is they're less.
Yep, exactly.
Yeah.
So the dispersion is greater in this town. The dispersion is smaller in this town. We'll call this dispersion standard deviation. Standard deviation is the average distance of each data point from the data mean. So on average, how different is your salary than the average salary?
Would you just say again? Repeat that thing.
It's written down on the next slide.
Okay.
It's the average, yeah, I did it right once. That's all you get in this. Standard deviation is approximately the average distance between the individual values in the data set and the data center. So this has a large standard deviation, this has a small standard deviation. Large standard deviation here, small here. Alright, so we might need to calculate standard deviation. We'll go over how we do it right now. If you want the population standard deviation is notated with this funny looking O, sometimes called sigma, O with a hat on it type deal. Remember this little U symbol, mu? What is that? The mean, right? So this xi, that's an individual data point. So what you'll do is for each data point, you'll take the difference between that and the mean. You don't care so much if it's positive or negative and you want to know the scale, so you square it. So take the difference, square it. Do that for every single data point, add all of those up. Divide by the total number of data points. And remember we squared the difference a minute ago? So let's get that back into usable numbers. So let's take the square root of all of that. And that gives us our population mean. Correction, I said population mean, I meant population standard deviation. Now, suppose instead we don't have access to all the information on all the points of data. We just have a sample, in which case we will take a sample standard deviation, notated with a lowercase s. So we'll take, remember this little x with a bar over it? X bar? What is that? Sample mean. Alright, so we sample 100 people in this town. We get a sample average income. We take the difference from each point in our sample and the sample mean. Square it. We divide by close to the sample size, but actually a little bit less than the sample size. Lowercase n is the sample size, so we divide by n minus 1. Now when you divide by n minus 1, a smaller number in the denominator here, that makes the whole thing a little bit larger.
Correct.
So that gives us a bigger interval for our sample standard deviation. The reason we want a bigger interval is because we don't have all the information. We just have a sample. So we make a wider interval, what will later be our confidence interval. We'll just have to give a wider estimate of what we think we know. Population standard deviation, sample standard deviation. Let's do an example. Suppose you had 3 employees producing widgets. Over the course of one day, they were able to produce 3, 6, and 7 widgets respectively. So employee 1 produces 3, 2 produces 6, the third employee produces 7 widgets. What is the population standard deviation of widgets produced? Take a look at these 2 calculations. Tell me how we're coming out to 1.7 widgets as our standard deviation. Who can walk me through these first 2 steps? What do we do here? What do we do here?
They put in the parentheses, they added that in parentheses first.
Yeah.
Plus 6 plus 7,
Yeah,
and then they got 16, and then they divided it by 3.
yeah.
That equals to the 5.33.
And what's that 5.33?
That's the percent.
The mean. Okay, we need the mean because we want to know the average difference of all of these from the mean. Alright, and what do we do here in this line?
Each number subtract one.
And then divide to the second square root.
Yep, divide the whole, take the difference between each and the mean, square it, divide by 3, square root the whole thing, we get 1.7. Alright, make sense? Now suppose instead these 3 employees, they were just a sample. A sample of total of 16 employees. I want the sample standard deviation notated with little x. How am I going to calculate that differently?
Like the first one, you divided by 2, the same thing, but instead of divided by 3.
3 minus 1.
So we divide by that smaller number, makes the outcome a little bit bigger. And for the sample standard deviation, we want a little bit bigger to account for our unknown factors. Alright, you got it. Population standard deviation, sample standard deviation. Alright, so let's look at these 2 sets of data. We've been talking about the height of trees in Canada for some time. So suppose some researcher has measured all 80 million, 40 million, I don't know, how many million trees do you think there are in Canada? 200 million trees in Canada, right? And the researcher has plotted that on a frequency distribution and found that it looks like this. There's an average height of the tree, there are tall trees, there are super tall trees, there are super, super tall trees, and then there is the exact same thing on the small tree size. Similarly, a researcher in Australia is looking at the size of newborn babies. There is an average length of a newborn baby, and there are babies that are a little bit taller, or a little longer, babies that are a little bit shorter. Take a look at these 2 graphs. Do they both look normally distributed? Alright. So yeah, good. We think they're normally distributed. There doesn't seem to be any skew going on. Now suppose these 2 researchers were on the phone talking to each other. They're describing, hey, my graph looks like this. Oh, my graph looks like this. Well, I have a smaller standard deviation because I'm dealing with babies. Right? Babies, like, 2-inch difference is a big deal. Right? So that's, they're closer in height. Trees, maybe like 10 feet is not a really big difference because trees can be huge. They're like, okay, well, it's a little funny that our graphs look pretty much exactly the same, but of course they're different. Because I'm talking about trees, you're talking about babies. And then suppose these researchers get the idea. Let's adjust for the difference in scale. Let's account for the difference in standard deviation between trees and babies. So let's put them both on a curve where we say, all right, let's make my average height of the tree the center of the frequency distribution and call that a mean of 0. And then the other researcher says, well, let's make my average height of a baby, or length of a baby, the mean of that frequency distribution. We'll call it 0. All right, and then I'm going to put all the trees that are within 1 standard deviation below the mean and 1 standard deviation above the mean. I'm going to put them in this quadrant. Okay? And the researcher in Australia says, I'm going to do the same thing. I'm going to put all the babies one standard div below, one standard div above, and put them in the same quadrant. What did these two researchers discover when they did that? They're the same. Yeah. They might have been a little surprised when they saw this similar looking distribution, but when they put them on the same graph and accounted for the differences in size or scale, then they were exactly the same. And then suppose the person in Canada says, just out of curiosity, what percentage of your babies are within one standard deviation of the mean? The person in Australia says 68.3. And the person in Canada says, what a coincidence. There's 68.3% of my trees are within one standard deviation of the mean. Crazy, right? So what do you think they did when they found this out, when they discovered this?
I guess they put it together.
They're like, this is great. This is a law of nature. We have discovered something. When scientists, mathematicians first discovered this, they thought they were hearing the thoughts of God. They thought we have found the secrets of the universe. That exactly 68.3 of all subjects in a pool of data will be within one standard deviation of the mean, as long as there's nothing skewing this population. And they found this over and over and over again. And they said, oh my God, this is amazing. So, law of large numbers, law of probability, law of nature combine to where many natural phenomena fall into this normal distribution. Trees in Australia, trees in Canada, babies in Australia, just two examples. When we can assume things are normally distributed, we know many things about that pool of data. We know that 68.3% of the subjects will be within one standard deviation. 95.5% of the values will be within 2. 99.7% of all the values will be within 3 standard deviations. We know these 3 things. We also know everything in between. We know what percentage of trees will be within 1.2745 standard deviations. And that is the exact same for babies in Australia. Why do we know this? Well, we know it 2 ways. One, because I was kind of joking about it, the researcher in Canada and Australia talking to each other on the phone and saying, wow, isn't that a crazy coincidence? They discovered this over time. They said, these are the numbers that are within 1 standard deviation, 2 standard deviations, 1.2 standard deviations. And then they started to do mathematical tests like you all did with the coin flip example. Remember how I reminded you that you're the ones who calculated the likelihood of 16 heads coming up out of 20? You did that. All right, that's what mathematicians did when they were calculating these numbers just to confirm them after they got all excited when they found them by accident. All right, so how are we doing for time?
7:52.
All right, we'll take a break. Yeah, let's come back at 8:05. Does that work for you? All right, excellent. I'll see you at 8:05.
Hey, Tom. How are you?
How are you?
Good, how you doing?
I'm okay.
Yeah, I was expecting to see Roxanne to come to.
Yeah, I don't know much.
She didn't make it, right?
I'm gonna go get another chips.
Alright.
She was supposed to, I think she was supposed to come to us.
Yeah, because, when he was going through the emails, she was on the list.
Oh, yeah. I need to confirm. I like him. He speaks so clear and reasonably clear and understanding.
For that. Yeah, it goes straight, make a right.
Go ahead.
I was like, oh, Lord. They go that crazy one right there, I'm sorry. So when I walked, it just didn't say anything, I went to the bathroom. Then when I saw right here,
bring it in the house, and I want my daughter to look at this book.
then my pastor, because I'm from, she said, you can put it on, I was like, no, I don't try to do it. Pastor. Because I've been here. You have to wear
I was here too, I went to the fish house.
She's like,
That fish was
I
good.
said, when I do see somebody here, from my other side, but doesn't mean that we all have the same kind of skill. So she said it wasn't instruction for Mac, it gives them 3 quarters. Oh, Lord.
You call her to see?
No, I'm calling one of my coworkers. I had a date, I had a dad, I had a day, so got a job.
But you.
I got fed up. I was like, that's it, that is it, that's it. I am not dealing with this child again. I was like, y'all handle him. I'm gonna write me a letter from top to bottom. You like this Florida? He can't, let me see how high your shoes are. That's not about you yelling in front of the kids. Grandson, right? I was like, first one, sit right here. I was like, don't yell at me.
She was telling me, I told you Casey called me twice, and that's why I told you. That's the thing, and we was on the phone all the way to to school. It's just, you know, 200, she got that's how things is going right now. She's like, oh, she's talking about her car. Her car.
Literally tells you that exactly how to get answer. It's really easy. It's really easy.
Like I printed it out and it's like, I have no idea.
Yeah, but it's like step by step.
Yeah, but it's saying when you add in.
You did the add-in?
Yeah, I leave it against really bad. It tells you on the previous page.
Yeah, I saw that.
Yeah, right here.
Yeah.
So you click, so you go in here. So, okay, so the input is the numbers. So, oh, well, you're in the wrong screen. You see? You go here, black. So you put, which function, oh, anything. Here. And then the script is statistics, you click okay.
field and
Calculate the output range, so you click here, and then basically you're clicking like where you want it to put the graph. So you just like click on here, whatever. Highlighted the whole thing. And then it says here to put summary statistics, so you click that, and then you put that. You can do something, and then you click here. Thank you so much, but yeah, it just, it's like each one, yeah, the next one you have to go to the next tab on the thing.
Thank you.
Do we input this into Blackboard when it's finished?
yeah.
Can I shoot something? Y'all could've got it, how you do the exercise, yeah, it's on the book, right?
I have, yeah, but we got the textbook on
Oh,
the e-textbook.
I've been trying to get that, all right. How y'all get the e-textbook? Computer, y'all stop playing.
On Amazon.
Y'all keep saying that to him, Amazon, I go on Amazon, I
They
try to
have
punch it up.
different options when you get to the book.
Show me, because y'all damn kids, boy, y'all be knowing how to do all type of stuff. Yeah, kids, man. I did it go, my hurt shot. Show me how to get it to Amazon, how you do that Amazon. But everybody keeps saying Amazon, it's not easy.
I had a cheeser.
Check? I
Yeah.
didn't find it on
I
Check.
found it on Check today. I bought it
The
today.
e-textbook?
Yeah.
How much?
It was like 60
Yeah.
It's expensive.
You say cheap?
I know, but I'm saying.
No, I mean not to be easy.
Yeah, and then
That's a high hundred.
$60.
Really?
I heard if you have the membership for Check, you can download like how much.
Oh, yeah, they have like all answers and stuff like that. I think it's 14.95 or something. Yeah, it's not too bad.
Oh, just be a member for.
Yeah, I just have for.
Usually what though? I know Kelsey's a beast on Excel. I was doing it manually. When I go home for no reason.
So you rent
square
it
it
right
once you get
now,
to the.
and you download like the whole crew, you download Amazon Kindle.
I'm with Roxanne actually, even though it's not still.
Oh, yeah.
Yesterday, so.
If you have a Kindle, yeah, you, once you download
So I
the,
can operation.
you download, yeah, you could
I
probably
was
do it,
also.
you download the Amazon Kindle app,
They-
and you log on to your Amazon account,
We
and
keep-
it's in there.
Oh, no, I
like
got
it's
both.
saved to your library.
Really don't have.
Like the e-textbook?
Yeah, but I read.
Oh, yeah, so wherever it is that it should be in there,
No.
like on the
Plus the standard deviation,
That's why
that's.
it's only to download, I never did that.
Look at that, I can
Last
just
time I
go
scored,
on
just
that.
give me
Yeah.
So order stuff, so then I download the app from there, and that's what.
This is-
That's
square, that's square. What do you-
And I went in there,
Wait.
and then it was
So
just
the-
like, I signed in, and the book was there.
Deviation, standard deviation, square.
Now it's here on my computer, yeah.
You can print it out whenever you want.
I don't know if I can print it, probably.
Oh, you
This
pulled
is
the
the paper right here? This is the book for today?
Yeah, this is the book.
That's for chapter
Standard
2,
deviation.
This is chapter
Right,
6.
that's right. And then this one is standard deviation squared.
It's
So
pretty easy.
how do you figure it
Right
out?
here, it tells you step by step exactly what you do that.
Can I fix, take a picture of
Yeah, it's a
chapter?
lot of
Excel
them.
for everything?
Yeah, this is the first.
That's great.
I don't know why they do it.
I just swear it.
So where do you find the formulas for those things? Where you find
On the bottom.
Oh, and White High.
Hold on.
The second question.
All the same formulas?
For this.
You want me to take it?
Yeah, I got it. Yeah, I got
Yeah,
it.
click on the function.
I'm telling people taking pictures and
Like that,
everything.
thank you.
Only thing I do, it's the same thing with my car. I used to get how when the gas is on, right? Sometimes I be going to the gas station and it be slipping through.
I think that's the other day. Because I got a new car and I was like, I don't know what side it's on, but now next to the gas thing, it has an arrow pointing to which side it's on. So I was like, oh.
Yeah.
I went to the gas station and asked the guy, I'm like, which side is it on? He's like, this. I was like, so embarrassed.
Well, I don't know because I.
It's on the dashboard, you
It
see
was my
it?
first time putting gas in the car.
Yeah. Oh,
Really?
What dash? What dash?
It's in front of you. So it's at the level of gas, right? Have you seen it says right on there? It should be a arrow pointing left or right. And where it's pointing means that the gas.
I dropped it.
Oh,
Which side of the gas?
I got two cars, both 2017, and I seen it and I thought they were telling me that I was taking it left. I'm taking it right, because the escape is on the right and the fusion is on the left. So I thought it was, I thought it was the arrow, and I kept hitting the arrow to make left right. I was wondering why it wasn't going off, and I forgot.
Just read the manual.
My manual was still wrapped up in the plastic. I tell you, I get the car out the line, I just drive it.
Oh Lord.
I know how to do the fucking car. I swear, you see, I didn't even get up to the book. That's bad. That's bad. My baby said, he said, so since he's but I just want $8,500.
Oh, did that one?
I said, where's the one? That's how she was showing me something.
How long did it take?
Roxanne? The damage? Joanne's here, yeah.
Thank you. Sorry I was late.
Alright, no problem. Nicholas Fitzgerald. Ronald.
My book hasn't come yet. I just really don't want to buy the
And I tell my son, no, I tell my son, hello?
Alright, so let's pick this up again. Before the break, we were talking about the normal distribution. And we said, hey, what if a researcher in Canada and one in Australia, they both say, I'm going to take my population mean, whatever it is, trees, length of, height of trees, length of babies, I'm going to call it 0. Then I'm going to take my population standard deviation, that's the average distance from each data, average distance of each data point from the data center, and I'm going to call that one standard deviation on the normal distribution. Guess what? Our graphs look exactly the same, and the percentage of data within each given standard deviation is known. What might be causing this? What factors might cause a normal? There are many factors that might cause a frequency distribution to be skewed. In the absence of these factors, the distribution will be normal. So we talked about a couple things that would skew a distribution. One super rich person, one community of comparatively much more poor people. Suppose in Canada there might be some nuclear power plant along the coast, or a bunch of nuclear power plants that are causing the trees to be smaller or bigger. Something like that might be going on. In absence of those things, a lot of populations will be normally distributed. So as a researcher, you just need to look at that. You need to say, is there anything that could be skewing this data? Does it look like it's skewed when I graph it? and you'll just make decisions about how confident you are that this distribution is normal. And when you give your final answers, your presentations, you'll say these are the assumptions we made. When we talk about sampling, we'll learn a technique which allows us to assume that the distribution is normal, and then we get to make some exciting assumptions because of that. Just a few points on the normal distribution. This guy, Karl Gauss, a 19th century German mathematician, he was the one who discovered this normal distribution. And he had those thoughts that we were just kind of talking about, where he looked at patterns and he said, wow, they're the same. When I'm talking about one population versus the other, the graphs look the same. Isn't that amazing? He's the guy who made those discoveries. Many natural phenomena have patterns that resemble or are exactly the same as the normal distribution. We are now ready to talk about z-scores. Z-scores apply to normally distributed data. A z-score is the number of standard deviations a particular point of data is above or below the mean. So if I have a really tall tree, I might have a tree with a z-score of 2.4. That means that tree is 2.4 standard deviations above the mean. If I have a really short tree, I might have a tree with a z-score of negative 1.2. That means that tree is 1.2 standard deviations below the mean. How we calculate the standard deviation, the z-score, x is the particular point of data, the actual tree or the actual baby. What is this?
The average.
What is this? Standard deviation. So we take the difference between the actual point of data, subtract off the mean, divide by standard deviation, gives us number of standard deviations above or below the mean. We can use the z-score two ways. One, we can say, well, if I have a tree with a z-score of 2.7, I want to know how likely is it that a tree is taller than that? Or how likely is it that a tree is shorter than that? So 2.7 is pretty big. There might be only 2% of trees in Canada that are taller than that particular tree. Any randomly selected tree would have a 98% chance of being shorter than that particular tree. That's one way we can use the z-score. Second way, you might say, I'm just curious. I want to know how tall a tree needs to be in the 80th percentile. I just wonder what that is. Well, you look on the z-table, and you'll find out what it takes, what z-score you need to have to be in the 80th percentile. And then you'll say, well, I know what the mean is, I know what the standard deviation is. I'm going to solve for the actual height that that tree needs to be. So two ways. Suppose I were to tell you I have a tree with a z-score of 1.2. And I would now like to know what percentage of trees are shorter than that tree. So you're going to need to look at the z-table. And the z-table reads cumulative probability. Meaning, whatever percentage you see when you look up a z-score of 1.2, it's telling you that's the percentage of data that is below that z-score. So how the z-table works is you'll look in the left-hand column for the units digit and the tens digit of the z-score, and then you will go over the appropriate number of columns for the hundredths digit. So 1.20 just means we go down to 1.2 and over to the 0 because the hundredths place is a 0. If it were 1.23, we would go 1.2 and we would have to go over to 3. But for now, we're at 1.20. Tell me about that 0.8849. What does that mean?
88%. Sorry.
Yeah, yeah.
Okay. Yeah. 1.2 on the C score. The majority. I mean, we can find the 88% for I mean 49% of majority of the trees belong to the 1.2 on the deviation kind of thing.
All right,
Sorry, I got a little
feel like
confused there.
You're on the wrong track, but it's put it together for us. Oh, you're on the right track. Did I say wrong track? I meant right track.
Right.
You're on the right track. Sorry about this. Go ahead. Exactly. All right. When you look at the z-score, this tells us the area under the curve below that z-score. So, if I have a tree with a z-score of 1.20, 88.49% of trees are shorter than that tree.
Right.
This tells us the cumulative area below 1.2, 88.49%. Now 88.49% can be written as 0.8849. Exact same thing, you're just going to need to be fluent with that. A proportion can be written between 0 and 1, but it's exactly the same as between 0% and 100%. Now, what if, let's do a couple quick little examples here. What if I have a tree with a z-score of 1.54? What percentage of trees are shorter than that tree? Yeah, so what did I say, 1.54? Yep, all right. So 93.82% of trees are shorter than that tree. Okay? What if I have a tree with a z-score of 1.85? 96.78% of trees are shorter than that tree. What percentage of trees are taller than that tree? What percentage are taller than that particular tree?
Oh, at 3 point something.
Yep, 3 and change. Exactly. It's because this 96 are shorter and there's only 100%. 100% is all trees. So there's 3 and change left over. Okay? Great. Let's do this male height example. And we'll just make sure we're feeling comfortable with reading that z-table. Suppose the mean height for an American male is 70 inches, and the standard deviation is 3.5 inches. Assume that the standard deviation is normal. Suppose Evander Holyfield has a height of 74.5 inches. What is the z-score that represents Holyfield's height? Please crunch that out for me. Feel free to confer with your team. Check on the video too. All right, what does it come out to?
80.29.
How much?
1.29.
1.29. How do we like 1.29? Alright, so the Evander's height minus the average divided by standard deviation gives us 1.29 standard deviations above the mean. What is the probability that a randomly selected American male will be shorter than Evander Holyfield? Next guy who walks by the door, what's the likelihood he will be shorter than 74.5 inches?
90.19%.
Alright. Yep, so you're going to look on the Z table, right?
Right.
And you're just going to look for 1.29, and whatever percentage it says, that's the answer. So what do we get for percentage?
90.15.
90.15?
Yeah, 90.15.
Okay. Are we all comfortable with that? Nice. Suppose Manny Pacquiao
Thank you.
has a height of 66 inches. What is the Z-score for Manny Pacquiao's height? Crunch that one out for me, please.
Wrong with that negative number.
Is it? What does a negative number mean?
Okay.
It's below the
It means it's below, it doesn't mean it's skewed, it means it's below the mean. And it is in this case. Yes. Manny Pacquiao is below the mean, so he has a negative Z-score. Alright, so what do we get for an answer for the Z-score?
Negative 2.5.
1.14.
Negative 1.14?
Yeah.
I like that. Okay, so Manny Pacquiao is 1.14 standard deviation below the mean. Alright, what is the probability a randomly selected American male will be shorter than Manny Pacquiao? 12.71? Alright. How did you get that?
I would say 87%.
Yes, yeah, so this is a negative number. So we're going to have to do something a little workaround with the Z table, because we don't have negatives on the Z table, right?
No.
What do you see when you look up 1.14?
87.29.
87.29. Alright, so what does that tell you?
That's where Manny Pacquiao stands, right?
What's that?
That's where Manny Pacquiao stands on the app.
If he had a Z-score of positive 1.14, that means 87 point what?
49.
49.
No, 29.
29? Percentage of the data is below that. Alright, well lucky for us, the Z table is symmetrical, and we can use this positive Z-score to reverse engineer the negative Z-score. So if 87.29 is below this, what percentage is above? Right, what's that little tail? What's in this tail right here? 12.71%.
Correct.
Excellent. So if we were to look at the symmetrical opposite and say negative 1.14, right, and then we've got the small tail here, and we've got all the rest up here, how much do you think is in that small tail? 12.71. I like it. So the answer to the question, what is the probability that a randomly selected American male will be shorter than Pacquiao, is 12.71. Fantastic. All right. What is the probability that a randomly selected American male will have a height in between Pacquiao and Holyfield?
77.4.
How do we calculate this?
Difference between the two.
Let's take the difference between the two. I like it. Erase this, make some room. Actually, I'm going to go over here. So, we know that Evander Holyfield is here, and we know that 90.15% of people are shorter than him. That's not our answer though, because that includes everything that is shorter than him. We want to subtract off this little tail, Manny Pacquiao, because that is not in between, that's below. We just want the stuff in between. So how much do we need to subtract off? Fantastic. So 90.15 minus 12.71 equals?
77.44.
314?
44.
44. Okay. 77.44%. That is the answer to the probability of the next guy who walks by the door being in between Manny Pacquiao's height and Evander Holyfield's height. Is there someone walking by to ask him how tall he was? Okay, any questions there? Good, good, good. Let's try another one. I think you've got the basic idea down. This is just a chance to get used to reading this Z table. A chance to maybe explain it to your teammates. A chance to bounce some questions off me. And this is exactly what we need to be doing at this point in the course, is just getting familiar with reading this. This can be a little bit complicated when you first start to learn it. So why don't you go ahead and turn to your teammates and see if you can answer this question. Suppose, actually yeah, go ahead and turn to your teammates, read the question.
And a standard deviation of 3.6. What is the probability that an individual flies between 19 and 26 miles per hour? So,
I'll try it with doing it, subtracting it and divide it. Okay. I'm curious to see. Sure.
divided by 3.6 equals
I'm gonna subtract it and see what comes out. And see if we do like 2 each. I'm just curious. You can't round up.
So 555, Z-score is...
It's negative.
Sure. You round it to the nearest digit. So, and that's negative, right? It's negative, negative 0.5. So it's negative 0.55555. So you round it to 0.55556. And it doesn't, yeah, so you need a Z table. Here, let me use a Z table.
So you have to do that. Yeah.
Maybe let's do this in some. Alright, I have a more extensive Z table for you. The one you have only goes, it starts at 1. Starts at 1. Alright, so this one goes up to 3.4. Anyone, okay. Alright, everybody has that wrong. More extensive Z table. More extensive Z table.
Thank you, sir.
You bet.
We've done well until we realize we need to.
More extensive Z table, alright.
Is this in the back of the book?
It is, yeah. Yeah, you can use the one in the back of the book. It's on your table. It's, you've got pages here.
So we found a terrible 0.5.
This is, and you actually have a negative one. You don't have to do that 1 minus. You can use the negative 1 and the positive 1.
But we go to 5.5, we don't go to 5.6, right?
Is negative
This is 5, 5, 5, 5, 5, 5, 5, 5, 5.
Just
We don't
round
go
it.
all the way down to the 6.
You'd round it to the nearest 2 digits.
Yeah,
In
so
this
it's
case, it
5.
would be
He said round.
0.56.
Exactly, yeah, so it's
Point
negative
You want us to
0,
round.
0.56.
Yeah, you round to the nearest 2 digits because you can only look at 2 digits here.
So in the case of
Oh, yes, I'm looking at 1.5, right?
1.5,
Oh, right.
1.3888. Because you can only look to 2 digits on the Z table, so you want the best 2 digits possible.
Yeah, but if you calculate, like, look at the calculation. If you calculate, right, and calculate. Then I do 5 divided by, and I know you're going to look up. But my other one is not working. When I calculate, I go to 1.38.
Okay.
Do you tell me to round up to the very end?
No, I'm asking you to round to the second
Which
digit.
is 8.
Yeah.
So it's 1.38.
Alright, so how you do rounding is you look at the second digit and then you look at the number 1 to the right of it. If it's 5 or better, higher, you round this to a 9.
So you want me to round to the right.
If it's 4, 0 through 4, keep it as Thanks for reminding me.
I always remember. So we're gonna do 1.56. So the number I got was
And that.
0.7123. That's what I got.
Check your phone, okay?
That's the number after the first one. There's a negative value. I have 1.